We'll continue the discussion of functions in this module with the consideration of recursive function, which is a simple but very important special case of functions that also they may not be intuitive from a programming perspective. The idea is that a function as a tool for breaking down the structure of a piece of code, it can be used to call other function and those function call other function and so on. But a function can call in a way itself with different parameters. And so this way of calling a function, it's called recursion. So having a recursive function. Some mathematical functions are particularly well described by recursion. And so it's important to be able to write things like this in a recursive way. And then one can take the consideration of whether a recursive or an alternative way of representing the function may or may not be more efficient. One important optimization that has been built over the years in compilers is the fact that when a function, since a function allocate in the stack temporary information, if the last call of a function is the function itself, the recursive call, that's what we call tail call, and the compiler can optimize by reusing the information on the stack instead of allocating a stack that is deeper and deeper for every recursive call. And so even if in theory a recursive function may not be necessarily the most efficient way to implement something, given the proper optimization that compilers do, given that the recursive functions are so common, they could effectively, practically be way more effective than the superficial analysis would indicate. So just to give a practical indication of how the recursive function work, we'll focus on a couple of simple examples. One is the computation of a factorial, and one is the computation of the Fibonacci sequence. Now, a factorial of a number n is defined as the product of all integers ranging from 1 to n. So 1 times 2 times 3 and so on until we go up to n. And so if you write this in a, say, computational loop, we can think of this as an iterative computation of the function. If we look at how rewriting the formula, we can get n factorial, as you can see, equal to n times the factorial of n minus 1. And so, as you can see, this is kind of a recursive formula. The factorial is part of the definition of the factorial itself. And this comes from the fact that the sequence from 1 to n minus 1 is the factorial of n minus 1 itself. And so this can be used in the calculation of factorial into different ways. So let's look at things kind of in practice. So this would be a traditional calculation of a factorial in an iterative way, right? So here we read an input the number of which we want to do the factorial. And then here we have the loop where after initializing the factorial to 1, we loop through over the integer from 1 to n minus 1. Well, n actually, it's smaller than equal. And then the factorial is multiplied by itself and I. So this is kind of the multiplication, and this kind of build a series, and then we print the result at the end. Okay, so we can look at how this would work in practice. So we clean and build the solution, and then so no error here. There is just a warning, and this should be cleaned up later. Effectively come from the difference in type. Actually, we could fix it now if we want to. Okay, let's try again. Clean and build the solution. Now there is no difference in type between those two numbers, so when they get compared, we don't have a problem. And now we run the execution, and so let's say factorial of 5 is 120. Let's try again. Factorial of 3, that's an easier one, 6. Let's say factorial of 4, it's 6 times 4, 24. And then we execute again. Factorial of 5, 120, that's 24 times 5. So 20 times 5 is 100, 4 times 5 is 20, so 120. Everything is clear. So let's see if we can, how we can turn this calculation into a recursive function. And so we can take a version that is kind of more similar to the mathematical definition. So let's look at this. So we have factorial of n. So we have a function that takes the n as an input. And now, if n is greater than 1, we apply the recursive formula. So we return n times the factorial n minus 1. Vice versa, if n is not greater than 1, so basically if it's 1, we return 1 itself. So this is where we close the recursion. Okay, and so now instead of having this loop here, we can directly call the factorial, and so we copy this. So, and instead of running the loop, we can say directly factorial of n, it's equal to factorial of n. Okay. So let's see. We build the solution. Oops. Term does not. Oh, by the way, we have the type that does not match, and okay, here we. So here there is a conflict between the name of the function and the name of the variable. So we can kind of hide this part, can eliminate this part, and still we have a conversion from long to int. So let's fix the types. Oops. And how we got rid of the warnings, execute, and say we do factorial of 5, 120, I repeat factorial of 4, 24, and so on. And so here, obviously this can go away. And so here you can see that, first of all, using a function simplify significantly the main. And then here we have a very simple and clean representation of the factorial based on the mathematical definition. Now let's look at a somewhat more complicated example, the Fibonacci numbers. So those are actually defined with a recursive function directly. So for a sequence of Fibonacci number, the Fibonacci of index 0 is 0, the Fibonacci of index 1 is 1, and then the Fibonacci of index n is the sum of the two previous Fibonacci numbers. So this is kind of the initialization, and this is the recursive formula. So n depends on n minus 1 and n minus 2. So how this can be computed both iteratively and recursively. So this is the code for iterative computation. As you can see, typically in the iterative computation, we initialize T1 and T2 are the Fibonacci numbers, kind of as we go in an iteration, the current one and the previous one. And then the next number is the sum of the previous one, and then we set the index of the next one. As usual, we read in input which number we want to compute the Fibonacci for, and then if n is 0 and is 1, we return up to that particular point. Otherwise, we have this iteration where for each step we increment the index, we print the result, and then we shift through the numbers. So T1 becomes T2, T2 is the next term, and next term is the sum of the two previous one. So it's kind of simple, but you see all this code put together. And so as we compute the Fibonacci and up to index 3, 0, 1, 2, 3, you see 2 is the sum of 1 and 1, and we can try, like, for a good number, 0, 1, 1 this is the sum of the two previous one, 3 is the sum of those two, 5 is the sum of 2 plus 3, 8 is 5 plus 3, and so on, and basically you get the Fibonacci sequence. Now, how would this be if we wanted to do the computation in a iterative way, in a recursive way? So we can replace this with a recursive function. We call it fib. And so Fibonacci of an integer x. Now, if x is 0 or 1 is the number itself. Otherwise, we have again this tail recursion where we return the sub of Fibonacci of x minus 1 and Fibonacci of x minus 2. So in this code, effectively, what do we need to do? We could replace the print statement here. Let's see. Instead of printing the next term, we could do Fibonacci of the index. Okay. And now we can remove all the other part of the computation. We can rebuild the project. In this case, no warnings. And so we do a positive number 4, 0, 1, 2, 3, 4. So as you can see, we wrote the formula in a recursive way, kind of very simple. See the stopping term. This corresponds very clearly to the definition here, and then the recursion, in particular tail recursion, where we return the sum of the recursive call to the previous two numbers. Okay, and so having the explicit expression here gets cleaned up, and so we just call this. And what's nice is that we could also directly call a particular Fibonacci number without building explicitly the iterative sequence there. So you can compute for 10 numbers and so on and so forth. Okay, so this is kind of concludes this basic introduction of using recursive functions. And in the next presentation, we'll discuss array and some additional elements that we will need in our next exercise.